All right, so greetings from Houston. What I want to do today is talk about magnets. And the good news is you really don't need to do a whole lot beyond just play along. Um, since we're just barely starting this out, since you just did the test yesterday, we haven't really done anything with the math yet. I want to just get us started on what these magnets are. And I mean, I know what a magnet is. Well, kind of. Magnets are actually really confusing, and in physics, if we start to deal with them, magnets actually get really terrible. And so what I want to do today is introduce you to magnets as a physicist sees them. I want to do a basic introduction to magnets. Now, for that to work well, you pretty much just need to play along. Great. So let's start. Magnets. Magnets aren't easy. Magnets in physics are actually really hard. Magnets in physics are something we only really describe because so far, like with F equals ma, we understand dynamics. We understand we're working with current. We can build these networks and test them and play with them. And when we get to magnets, we know they exist. We know they're really important, like the motors and the lights and the electricity that's running through this room, and everything here has magnetic effects, and there's magnetic effects in chemicals, but we don't really understand magnets. I mean, we kind of understand magnets, and we're getting a better idea than we used to have, but really, honestly, we don't know mathematically that much about magnets, which is different than, let's say, electricity or anything else we've studied so far. And you're thinking, well, wait, this has been kind of a math class, Nedic. Why are we doing the not math stuff now? Well, because it's really confusing. Let me introduce you to some like weirdnesses of magnets. Okay, magnets are really, really powerful on the scheme of things. These are two neodymium magnets, elemental magnets, and obviously you can see you'd have no desire to put like your fingers between neodymium magnets, like violently strong, right? Yeah. Magnets are weird insofar as they're going to have some level of order to them. If you look, that impulse actually could travel through it. So when he first kicks it, I want you to watch this one more time. When he first bumps that magnet, you'll see a wave travel through. And then eventually one travels far enough to go on and start the chain reaction. Magnets are just weird. This is a ferrofluid. It's like basically jello with iron filings in it. It's a threaded screw there, and you can see the magnetic field is stronger at the tip, and there's something weird with the wedge shape of the thread going on it, and voila, like weird. Ferrofluids are really fun to play with. We might play with one a little later this year. Magnets confuse me. Here he's got some magnets north, south, and a little impulse creates a much larger impact. So a push, and somehow this is amplifying the wave to the spot where it's strong enough to push the can off with quite a bit of velocity. So, I mean, that's weird. There's energy coming from something there that's stagnant. Like, it's not how physics has worked so far. This is another neodymium magnet. It's just being eaten by a magnetic gel. You can see how it deforms in the shape of the field. Really weird stuff. Magnets will even deform electronics pretty firmly. You see this TV here, and then, okay, this guy's got a massive neodymium magnet. I'm actually relatively jealous. And he's able to push the picture off this old CRT screen. Like, what do you mean it affects light? Like, this is weird. This is weird. And apparently, it even affects the sun pretty firmly. This is a little animation of a sunspot cycle in 2011. And you can see the magnetic field lines here, the green, beige, and pink, orbiting around these black things, these sunspots in here. Weird stuff. And as a matter of fact, that same storm, I was in Minnesota at the time and took this picture of the Northern Lights. So somehow that effect there and this effect here were linked. And why I saw them in Minnesota and you didn't see them here in Kansas City probably links pretty much to magnets. Otherwise, we wouldn't be talking about it. So of course, my proximity to the North Pole mattered. But why something 93 million miles away could lead to something, a few thousand feet away is a strange question, for certain. Okay, you're familiar that magnets have north and south poles, opposites attract. If I have a magnet on a string, it's probably not going to do anything, but if I have a magnet floating on liquid, it will orient itself slowly towards the north. Neat. You know magnets. You've played with magnets. I don't need to tell you that. However, amazingly, as juniors and seniors, I will still have a student or two miss this question. So a quick reminder. North and south attract. North and north push away. Okay, we're good. Assume you're good from there. One thing you might know is that if you hang a magnet from a string, it probably doesn't do a lot unless it's a pretty weak magnet. However, if you take a cork and you put a magnetic needle on it and you float it in water, it's going to rotate itself until it's in line with the North Pole. Except we have a problem. Well, two problems. Apparently my face disappears, which is probably actually a piece of joy for you. And that we said the North Pole attracts the South Pole. And by definition, the needle which points north is the North Pole. So what we call the North Pole is actually the South Pole? Yeah. In other words, the North Pole of my magnet here is going to point at the South Pole of the Earth's magnetic field, even though it's pointing to the North Pole geographically. So that it's confusing because magnets are confusing. What we call north, magnetically speaking, is pointing north. That's very true, because there's a South Pole of a magnet there. But more even confusingly than that, because we know this is the North Pole, we're going to call the South magnetic pole the North Pole. Anyway, we're just going to call it the North magnetic pole, just to make things really annoying. I don't really care. But at the same point, it really entertains me that, we got to make up our own system, and we still messed it up enough to do this. Of course, what's actually at the North Pole is an interesting question. It's not this, I hate to break it to you. And it's not even this, which is the real North Pole. The North Pole, 0 every degree you go is south, blah, blah, blah. I mean, this is the actual North Pole. They took a nuclear submarine and breached the ice. Even that, not the North Pole. Dope, not the North Pole. It's not even this point right here. It's not. The North Pole, magnetically speaking, is way over here, kind of in none of it. Sure, if I'm in the central United States and I use a magnet, I point pretty close to north. Fair. If I'm at the North Pole and I use a magnet, the North Pole doesn't sit here and spin or anything. It points me south, because of course that's where the magnetic pole is. If I sit here in Alaska and I try to go, my magnet is not pointing me to geographic north. The north, south, east, west are off quite a bit. It's a compass error, and you have to account for it if you're using a map. Otherwise, you're not going to end up anywhere you think you are. Well, that's kind of the problem, actually. It's really far off. And if that weren't enough, okay, maybe it's just weird. Maybe geography is weird on a good day. But it moves, a lot. Not oh, it moved a mile here. No. It's moved from 70 degrees to 82 degrees in I don't know, 3 human lifetimes. What in the world is that? Besides annoying. And it's moving really, really fast. If you look at this, we have to keep updating where the North Pole is, because the North Pole keeps changing, which is really, really annoying. And so the question is, where is the North Pole? Well, it depends on when you're alive. And you can see it moves a ton. And you might notice these lines in here going through. These are more modern measurements. And the red line here, that's very obvious. That's the more ancient extrapolated measurements. If we think about magnets, we don't think about them moving around. We don't think about parts of our Earth changing, let alone on human time frames. These things are moving now. The planet doesn't tend to change on the order of centuries. It tends to change on the order of millennia and millennia. Stuff's weird. For the North Pole, the walking south from every direction North Pole, that isn't going to move. It's an oblate spheroid. It's not going anywhere. And yet the thing we actually care about in some ways, which is the compass north, is moving a lot. And if that weren't enough, I suppose it has to get weirder because magnets. And every so often the magnetic poles do something like this. Ooh, apologies. Sometimes they're 2. That's cool. Then things go crazy and they're like 3, and then the South Pole is now the North Pole. Because, that makes sense. Yeah, like the Earth's poles. And this isn't like, oh, it happened once. Like the Earth was having a bad day and we just flipped it. No. Like this is a consistent pattern. Like this happens in a relatively rhythmic way where the poles just flip. And like, again, in the middle of it, not only do they flip like into multiple parts and then they rejoin. I'm skeptical. Like, magnets are incredibly annoying. At some point, probably not in our lives, but inevitably not in our lives, the North Pole will actually be the South Pole geographically, so the North Pole will actually point at the North Pole, and no, it won't. It's annoying. And if you say, well, Nedic, this is really stupid and you're long-winded, no, this is really kind of cool. Like, something that you really thought you understood, you probably had a maybe passing understanding that, oh yeah, maybe the poles slip or something. You don't have a clue. I mean, we can talk about why we think this happens, things like flux lobes and things like lodestone. No. We don't have a clue. And yeah, it does happen pretty frequently. A couple times every million years. It's been a long time since the last flip, actually, and we can't predict when it's going to happen, and we know from some geologic records that sometimes it takes like thousands and thousands of years, and sometimes it takes like 10 years, because, predictability is prior to magnets. And I should point out, while it's been a very long time since it's flipped, it actually did flip for like 400 years and then go back because, magnets. Like, magnets are annoying. And I want to point out, like, there's a reason why we don't do math with magnets. It's because things like this bowl, where it's not even predictable and it can flip back and we don't have they're just weird. We do know these pole reversals happen because rocks actually can be magnetic. So if you ever thought about like a rock holding up metal, that's weird. It's called lodestone. Lodestone is how we discovered several things. People in early human history thought it was magical for obvious reasons. And it's a good source of a few pretty heavy elements. It's actually a really cool rock. But if I step back for a moment and think about metal being stuck to a rock like that, I'm going to make my statement be true again. If I had a magic wand that could show me magnetic fields on the ocean's floor, I'd see striping like a zebra, north-south, north-south, and I could measure how far apart those are if I knew how fast the seafloor were spreading, and it is spreading. And I would know exactly how long it's been since the last pole reversal, and by extension, using other things like positions of lodestones on non-ridges, I can prove, hey, by the way, this does prove the seafloor is spreading. This is a tautological argument. Both things reinforce each other. And, it makes sense. What's going on here is like the magma rises, and it's north at that time, and when the pole flips, the magma is still rising, but it's no longer north, and so the rock is going to orient itself differently, and because the magnet's cooling, it actually traps the magnetic field inside the rock. It's basically how lodestone works. Weird stuff. Weird stuff. Weirder stuff is magnets don't work like you think. Like, okay, here's a north and a south magnet, right? And you think I could go take this to a saw and go buzz, 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 and have a north magnet and a south magnet. Makes sense, right? No. You just get 2 magnets. You want to do it again, you get 2 more magnets. You can keep just splitting it. And to the best of our knowledge, you can't split it small enough. Like, oh, I got the north atom here and the south. No. Even the atom might exhibit paramagnetic properties. That's a magnetic monopole, in other words. I can't just have a pure North Pole or a pure South Pole. Sorry. You can't do that. That's called a monopole. It's off limits. Don't make monopoles in my class. You're going to make me hurt inside. Okay, so if I have a monopole, I'm no good. I have to have a north and a south, otherwise I don't have a magnet, which actually gives us some hint as to how they do work on a basic level. Now we're familiar with electric fields, but actually we can make a magnetic field, which we call the capital letter B, just to confuse you. Capital B, magnetic field. Capital B, magnetic field. So here's a magnetic field from a bar magnet. Magnetic fields can do work, they can store energy, they can change intensity. They're very similar to gravitational or electric fields, except they're caused by magnets, which makes them very annoying. In grade school, you probably took some iron filings and put it on a piece of paper and stuck it on a magnet, and you got to see a magnetic field, something like this, where, oh yeah, the magnetic field goes between north and south and looks awfully like an electric dipole, now that we know what those are, by the way. Weird. Probably just a coincidence, right? Well, maybe. It's a dipole, a high and a low, right? There's a high here and a low here. But, yeah. And there's some link between these, but some key differences too, one of which involves the magnetic field inside the magnet. Anyway, you can see the magnetic field starts at the north and terminates at the south and makes closed loops, and it really will do that as much as it can. If I bend it into a horseshoe like this, you can see that magnets aren't linear and that the magnetic field is very much stronger down here than up here, which is nice because I'm trying to pick something up and I don't want the metal to whack my hand first, or I want to know exactly how it's going to work. Then, you know, having this concentrated field helps. And when I take two magnets of the same polarity and I try to push them together, like a south and a south, like this, I'm going to get repulsion, which looks awfully like the electric repulsion as well, right? When we learned about two positive or two negative Coulombic charges, electric charges that look like this, well, two positive or negative magnetic charges look the same. And this is really frustrating for physicists in reality, because there should be some mathematical combination that explains why these two things are similar, and there's some superficial explanations with like deeper math, nothing there. At least yet. All right. One thing that's weird is the field actually runs through the body of the magnet. So because the magnet has a shape and is a piece, we can't just pretend they're little dots. So this magnetic field here, I know the magnet's blocking it, but actually all of these lines, every single line in a bar magnet, every single one of these fields has to go through the middle of this, which is weird. So I should pause for a moment and explain the teleportation of time 15 hours forward. I just got back from the robotics competition day one. It did quite well, actually. And so I do want to apologize for the discontinuity, but I do want to pick up here. Like, when we're talking about a magnetic flux, we're talking about something that loops through the magnet. There's no start, no end. It's a circle. And so we exit the North Pole and enter the South Pole, and this makes sense. The flux on the Earth, in other words, starts up by the Arctic Circle and comes down to Antarctica. That actually, I think for the first part of this, actually is one of the first things that makes sense. So our B field, our magnetic field, is determined by the direction a compass would point, and it kind of flows along the compass. This is one of the few spots that is actually logical to me. And so if I look at this, I'm not sure which is north and south because, you know, there's no arrowheads. But let's just define this one as north. You know, the magnetic flux would come up, round, and through. And immediately something the student says, well, but look, this one's clearly not going through the road. Yeah, I know it's not going through the magnet. I've got you. It's a little more complicated what I'm saying, but we, in a mathematical sense, are going to have to pretend that it's going through the middle of that magnet. Imagine in three-dimensional space, maybe it's arcing across the top like this, and it makes more sense. Bear with me. I know it's a bit of a lie. Okay. We have two units of magnetism. Both of them sound familiar only because the scientists are familiar. The first is the Tesla. The Tesla is massive. Okay, a Tesla, the Earth is like 1/10,000th, 1/100,000th of a Tesla. It's an absolutely miserable unit. So we actually end up using the Gauss, even though the correct unit is the Tesla. So in class, you'll just see me use G and T. Just imagine them as magnet units. And we know that a G, confusingly, is the smaller unit. That being said, even though you probably have heard of a guy named Tesla, even though you probably have heard of a guy named Gauss, if you're interested in math at least, you probably don't have any clue what a 10 Gauss magnet is, and is that a big deal or not? Or, wow, that says 1.5 Tesla, should I be concerned? Well, I want to go through some examples. Okay, the bar magnets that you're used to, your refrigerator magnets, things like that, are somewhere between 10 and 100 Gauss. Okay, so that's our baseline. I know that magnet. That's 100 Gauss there. And actually, a sunspot, which is, a massive, bigger than the Earth magnetic, deviation on the sun's surface, is actually only about 10 times more. Which is weird. That I can't even feel from, if I had it in my hand here, it wouldn't have any impact on metal, in the hand here. And then, this has impacts literally larger than the planet Earth, and it's only 10 times bigger. And I want to point out that magnets are really different. And that's, nothing really. Like, okay, here we're up 15 times more, and we have a 1.5 Tesla magnet, which is an MRI magnet, which is strong enough to, pull your wheelchair into it. It's terrifying. It's called the missile effect. It's actually responsible for killing someone every so often. You can't have magnetic materials in an MRI room. Like, the magnets are crazy powerful inside of one. They're cooled with liquid helium. Like, crazy, crazy, crazy. And, powerful enough to pick the floor before. I don't know if you ever, picked one of these things up, but they're, heavier than a person, and it flung it through there. Crazy powerful. Yet, stronger than the sunspot? Theoretically, this is a video of, a chair getting sucked in, I guess. I don't know. At some point, they're pulling the chair, and yeah, okay, cool. They've got, a strain meter over here. And yeah, whatever. The point being is, okay, that is a crazy magnet. I've never encountered a magnet like that in my life. 60. Sounds like the sound. That's kind of annoying.
Ooh. We are at 600.
Yeah, it looks like, okay, so yeah, that's pointing like 1,300 pounds. It's cold. Crazy, crazy, crazy. And it looks like, ooh.
Baby! There we go.
Okay, well that's a crazy amount of force. It looks like 2,000 pounds.
Which is far more than this.
Crazy. Anyway. I don't care. And you can go from there. An even stronger magnetic field starts to exhibit what's called paramagnetism, and you can throw a frog in there and it'll levitate. Now, the frog is perfectly okay in this case, besides being confused as all get out. Sometimes when I see something like non sequitur, I love Douglas Adams and Hitchhiker's Guide, a whale just appearing and the short thoughts of the whale falling through an atmosphere. Well, I can't imagine myself in this frog's mind beyond, I suppose, maybe fun, but probably absolute and total disarrayed, chaos in reality. But yeah, if you get a strong enough magnet, I can actually levitate you easily. Then there are these things. Okay, that was 10 to the what, 5th? This is 10 to the, I don't know, the 11th, a million times more. It's called a magnetar, just a special star. It's hyper-magnetic. The universe is full of really weird and strange things, and magnetars are way up there in the world of weird and strange things. The magnetism here, okay, again, this is powerful enough to levitate you. This is a million times more. It's a million of those magnets stacked on top of each other. What in the world? Crazy. And it does have some weird things. I've used this word paramagnetic a few times. So this is liquid oxygen up here, I believe. Although normally liquid oxygen has more of a blue tint, so I'm not quite sure what's going on here. It's being poured between two anvils here. A very strong magnet. You can see this liquid, whatever paramagnetic liquid it is actually getting trapped between the magnets. And that tells you something about the structure of the molecule. There's some interaction chemically that's magnetically interesting, and this is in a chemistry class, and certainly in a high-level physics class, something's causing it. And so that's really weird to me. that a chemical can be this magnetic thing and be impacted by what we're talking about. Because when you think about physics, most of the time what something's made of it doesn't matter. I can make a penguin act the same way as, well, whatever else, a bowling ball, I guess. It doesn't matter. So paramagnetism is weird. The reason why I bring it up is when we start asking, well, how does a magnet actually work? We have to start asking this in chemistry. And certain materials, really iron, nickel, cobalt, there's something that looks random in most chemistry that ends up not being random. And it makes what's called a domain. A magnetic domain is something that I want to pick up with on Monday. A magnetic domain is kind of like a grain. It looks like this. You can see that zebra stripe pattern that we talked about with the sea floor. And you can see over here down at the bottom, this being a German scientist and my thing being in the way is kind of annoying. I don't know how to get that rid of. Anyway, at some point you'll see this is a neodymium iron boron magnet. So a very common rare earth magnet. And this little thing here is a domain. And this little thing here is a domain. And this little thing is a domain. It turns out in this magnet, these domains have some direction to them. And they don't cancel out randomly. We'll talk a little bit about why that is on Monday. That being said, this is already a long and arduous video, and I really don't need to sit here and talk more about domains. I mean, this stuff gets difficult. So what I want to do instead is go very, very quickly back and just kind of make the key points that I want you to hear out of this. And we've gone through a lot if you look. Okay, one, really big key points. Magnets are weird, and the north geographic pole is the south pole of a magnet, even though it represents the north magnetic pole. Whatever. Second key point is that magnets are legitimately weird, and the Earth's magnetic pole does move significantly, and we can use it to prove plate tectonics. Third, there's no magnetic monopoles ever. No monopoles ever. I will ask you that. Some of you are going to miss it, and it's going to make me say, but why? You can't have a monopole. You have to have a north and a south. Like that's it. There's nothing else I can do. Field lines run through the magnet. Field lines run through the magnet in loops without an end that point from north to south. So even though they are infinite, they're finite in terms of directionality. And most importantly, we have the Tesla and the Gauss as our unit. And we need to know that the Tesla is the larger unit and the Gauss is the smaller. With that all being said, this is already a long video. I think I'm happy with that. The introduction is done. When we come back in on Monday, we can pick right up from there. I'll summarize this again for you in 5 or so minutes, and then we'll move into what's a domain, how do you get a magnet, how do you actually predict some behaviors here, what do we know about this, and move into the really interesting thing, which is, of course, how do magnets and electricity relate, because we know this whole chapter is supposed to be about electricity. And so if I'm talking about magnets, apparently there's some interaction between the B field and the electric field, and where does that crossover episode happen? Where do we get magnetism and electricity to interact? And I'll tell you right now, the modern world wouldn't exist if it didn't, because magnetism and electricity are so inextricably linked in things like motors and generators and things that make our things work. Even the speakers that you're listening to this on right now are absolutely magnets being driven by electricity. And so many other things in the room around you. But you know what? It's a Thursday. You have a 3-day weekend. I want you to enjoy it. You have no homework. Absolutely thank your sub. And respect them. You have the rest of the period, how much ever is left, to quickly work on whatever you need to do, and I hope you have a great day. So, thank you. Bye.